Well, finally we come to lecture 5 on groups, which is what this whole lecture set, this course is supposed to be about. So the first 4 lectures were all preparatory or tool making. So finally we've reached the point where we can actually apply those tools and do some real group theory. Now before plunging into what a group is, explaining what the definition of a group, I'd like to play a little bit of a game. Marcus du Sautoy. Now this guy is a pure mathematics professor at Oxford University in England, and he gets on the media a lot. He's the guy who took over the job of Richard Dawkins, the famous, how can I describe him, radical atheist who's almost single-handedly converted about 1/3 of Americans to atheism. Anyway, so Marcus du Sautoy has taken over his job, and he's as I said, a pure mathematician. And he's rather famous for saying, in his view, the essence for him, the soul, the spirit of pure mathematics for him is what he calls pattern searching, looking for patterns, sniffing around inside mathematical phenomena, trying to find patterns that emerge, like in this particular case, in that particular case, and you know, what do they have in common, and can one extract generalizations from these phenomena and create a new mathematical entity, something like that. So I want to do that before just throwing at you the definition of a group. I'd like to try to evoke your sense of curiosity, because some small group of people, the pioneers of group theory in the early 1800s or so, starting with the 21-year-old Galois, who stupidly shot himself to death. Well, it wasn't a suicide, well, indirectly. I mean, he was in a duel. He was 21 years old, and the idiot got himself killed, and killed off one of the most brilliant mathematicians in mathematical history, one of the great tragedies of mathematical history. Anyway, so we've been talking the last couple of lectures on sets and binary operations on sets, and this particular and binary operation tables, like here's one, and we've actually done this one before, and I'll introduce another one of a completely different nature, like the nature of the set here are just integers, and the nature of the set here are so-called symmetry operations, and I'll explain a bit later what all that means. But what I'm trying to do here is to give you two sets with two symmetry operations, and they're wildly different in nature. The two sets are different. The two symmetry, the two binary operations are very different, and yet they have something in common. And the notion of group is about that commonality. What is it about these two very different sets and the binary operations that are similar? You know, what common features do they have? And that would be what du Sautoy would call a pattern. You know, they have something in common, and you try to extract that. And if you had lots of these examples, and I only have time to sort of mention 2, and space, but imagine you had lots of them, and they all seem to have this recurring pattern. And from that you generalize, you extract what they all have in common, and from that you form the notion of a particular kind of set, and you label it a group, and then you define what a group is. A group is a specialized kind of set that has this properties that all these kinds of sets with the binary operators have. Okay, so let's do that. So you may remember this from a previous lecture. It's a binary operations table, and the set is just 4 integers, 2, 4, 6, 8, and the binary operation on this set is you take any two, A and B, and you multiply them, you get the product, and then you mod by 10. Remember, modding by 10 means that you divide by 10 and you get the remainder, what's left over, and you put that remainder into the corresponding position of the table. So, okay, let's just do a few quickly. So, and by convention, right, from a binary operations table, this first column, that's the number that's your A, if you like A times B. So that would be your 4 different kinds of A, and that would be your B. And A and B both have to belong to the set. And the set is for integers 2, 4, 6, 8. Right, so AB, so let's binary operation. Now in this case, the binary operator is take the product and mod it by 10. Okay? Alright, well let's do, 6 by 8. So 6 by 8. So you look at the table. So 6 binary operation 8 gives you this one, 8. Okay. Let's try some others. Let's try 4 by 8. 4 by 8. That's 32 mod, so it gives you a 2. Okay. Okay, now just look at it. I mean, B de Sautoy, was that name French? De Sautois originally, I suppose. Anyway, have a look, and do you notice some odd things about this particular array of numbers, this square block of numbers? Look at this. Here's a row here, 2, 4, 6, 8, that is just the same as your set, right? 2, 4, 6, 8. And here's a column here also, 2, 4, 6, 8. Well, don't you find that a little odd? I mean, there's something peculiar about this binary operations table. And notice also for each row and each column, each member of the set is mentioned once and only once. There's no repeats. There's no, like you don't get 2 4s or 2 6s, or there's just one of each. Right? So we're noticing certain patterns about this binary operations table, and make a similar comment here. But we'll get onto this one a bit later. Now, what else do you notice? If I take 2 by 2, I'll get a 4. 2 by 4, I get an 8. If I take a 4 by 2, I get an 8. Now, there's something a bit strange about this 6 here. Watch. If I do 6 by 2, I get 2. If I do 6 by 4, I get 4. If I do 6 by 6, I get 6. If I get 6 by 8, I get 8. So it looks as though this 6, in a sense, is not doing anything, right? So in a sense, 6 by whatever it is, x, just gives me x. Okay? Now, what about the other way around? Try this. What's that? So something by 6. Something by 6. Well, 2 by 6 is 2. 4 by 6 is 4. 6 by 6 is 6. 8 by 6 is 8. So we've got something like that. So it looks as though this 6 here is a sort of a has no effect type element. Right? Now, we will call this 6 a unit element, for reasons that will become apparent a bit later. Okay. What else do we know? Well, it would be a bit tedious, but these operations, when you perform the binary operator twice on a triple, say something like this. 2, well, let's do it. 2, you're probably guessing I'm heading towards the concept that we talked about in earlier lecture, associativity, right? So, question mark, is this the same as 2, 4, 6? Is that true? Is this table Is this binary operator here, is it associative on this set? Well, let's do just a couple of examples. So 4 by 6, that's 24, so that's 4, right? If you mod 10, and this is 8 mod 10, 6, right? So quite different things. Now 2 by 4 modded, so that's just 8.